Ladies and gentlemen, the title to my presentation is Natures of Antioxidant Species for Static Methane Oxidative Coupling Reaction. This is the work of Xiamen University. Since the mid-1980s, methane's oxidative coupling to form high hydrocarbons has been attracting much attention. In this presentation, we call this reaction smoke for shocks. It is now generally stated that the smoke reaction is a heterogeneous homogeneous process in which methane reacts with active oxidant species on a catalyst surface to form methyl radicals. And methyl radicals mostly emulate into the gas phase where they compose to form ethane, and ethylene is produced from ethane as a secondary reaction product. In the mechanism studies, viewpoint given in the literature concerning the active oxidant species responsible for initial methane hydrogen attraction reactions are significant controversy. Several types of oxidant species have been suggested to be responsible for methane's activation. There are peroxide species, superoxide species, and O- species. Those other oxidant species has been suggested. The purpose of our work is to study the natures of active oxidant species in MOX reactions. In this work, we first study the promoter effects toward C2 product activities on limestone oxides for MOX reactions. Then the tendencies of alkali metals and alkali metal catalysts to stabilize the superoxide species. Finally, the reactivity of the superoxide species towards methane at the MOX reaction temperature. The results of our work suggest that the superoxide species is active and C2 selective oxidant species in MOX reactions. First, we studied the promoter effect of alkali metal sulfates and alkali earth metal oxides on limestone oxides for MOX reactions. The lithium, sodium, potassium, rubidium, and cesium sulfates promoting limestone oxide catalyst was prepared by impregnation method. It can be seen from these figures that the alkali catalyst promoter effects increase with increasing cation size or the promoter catalyst. Next, we study the alkali earth catalyst promoter effects on limestone oxides. This series of catalysts was prepared by drying and emissions of freshly precipitated carbonates of limestone and alkali earth catalysts. It is also finds that the promoter effects of this series increase the increasing cation size of the promoter catalysts. It has just been indicated that the alkali metals and alkali earth metal catalyst has a strong promoter effect on the limestone oxide towards the MOX reaction. So it is interesting, and methane is activated by the oxidant species on a catalyst surface. So it is important to study the tendencies of alkali earth and alkali metal catalysts to stabilize the superoxide species. We know that alkali metals and alkali earth metal can form oxides, superoxides, or peroxides with oxidants. The Raman spectrals of oxidant compounds of lithium oxide, oxidant compounds of lithium, sodium, potassium, and barium was given in here. The bands in this region can be assigned to the overall strength of superoxides to the peroxide species, and the bands in these regions can be assigned to the CO tracks of carbonate species, and the band in this region can be assigned to the CO tracks of the superoxide species. From this figure, we can see that on the lithium oxygen compounds of lithium, there was neither peroxide species or superoxide species on these oxygen compounds. However, on the oxygen compounds of sodium, potassium, and barium, there were both peroxide species and superoxide species exist. To establish the molecules of peroxide species and superoxide species in this oxygen compound, temperature probing decomposition spectra were performed. By calculating the two decomposition peaks of the TPD spectra, we can estimate that the molecules of superoxides and to peroxides in oxygen compounds of sodium is 37 to 90 to 63, and that of potassium is 90 to 10, and that of barium is 16 to 84. And from the knowledge of chemical knowledge of peroxide and superoxide, we know that the oxygen compounds of lithium is the combustion oxygen products of lithium is oxide, and magnesium and calcium is oxide too, and that of cesium and rubidium is superoxide, and that of strontium is oxide and peroxide with trace amounts of superoxide. Thus, we can see from these trends that with increasing canal size of alkali metal canides and alkali metal canides, the strong is these canides' abilities to stabilize the superoxide species. Then, we studied the relativities of the superoxide species towards methane at a moderation temperature. Methane this reaction was performed by ESR spectroscopy methods. The oxygen species on the lanthanum oxide promoted thorium, that is an active catalyst for moderation, was taxed. The sample was treated at high temperatures and quenched rapidly into the liquid nitrogen to trap the species on the high temperatures. When the sample was treated by oxygen, the thinness recorded can be assigned to the superoxide species. However, when the methane was introduced, when oxygen treated, the thinness disappeared. This indicated that at the more recent temperatures, methane superoxide species was related towards methane. Discussions. Different kinds of oxygen species reflect different types of catalytic performance. Although it has been reported that at this temperature, superoxide species did not have the ability to activate methane. However, the experimental results of Oxidative and this work indicated that at a more recent temperature, superoxide species became active enough to react and activate with methane. Peroxide O- species and peroxide species are more reactive than superoxide species towards methane. If we suggested that O- species and peroxide species are the essential active oxygen species on the catalyst surface, responsible for methane reaction. It is difficult to explain why the high reaction temperature, which is needed for more reactions. Oxygen species on a catalyst surface not only take part in the methane activation process, but may also take part in the further deep oxidations of reaction intermediate and reaction products to produce unstatic reaction products. You can see here the O- species and peroxide species is more reactive towards reaction product ascenes than superoxide species. So they, in the more reaction, they will be too active to be static. While in these three oxygen species, the superoxide species, the less destructive toward the reaction product, that is active and selective. Oxygen species transform on a catalyst surface according to the general schemes. According to the reaction systems and reaction conditions, particular transformations may be fast or slow. It is important to know that superoxide species is the precursors of other types of oxygen species. Its half-lives can be prolonged by adding the oxide catalyst with some superoxide stabilizers. It has been known that ability to stabilize the superoxide species increase with increasing canary size of alkali metals and alkali metal series. Thus, when the large alkalis or alkali metals that had strong ability to stabilize the superoxide species was added to the oxide catalyst, the superoxide species, the half-life of superoxide species on the catalyst surface may be prolonged, and the opportunity to forming other types of oxygen species that is too active to be destructive may be reduced, and thus the staticity is increased. In conclusion, our work strongly suggests that the superoxide species is the active and selective oxygen species in the mock reactions. Finally, we would like to send the fundamental supports by the National Science Fundamentals of China. Thank you for attention.
You show the active oxygen species in superoxide submerged on the catalyst. Do you have any idea about the absorption type of this superoxide? Superoxide ion absorbed on other metal or magnetic absorption type? Where is superoxide absorbed?
On which side? I saw it.
Because if superoxide absorbed
on the oxide catalyst surface, the oxygen species often forms on the oxygen mechanics on the catalyst surface.
Yes, but catalyst surface means not like type or which type superoxide
the defect structures on the defect structure sides.
Sorry? Defect.
public medicine proceed more selectively without molecular oxygen by using only lattice oxygen. We don't. And there are many reports, and especially Fujimoto in Japan, oxidative public medicine proceed almost selectively without molecular oxygen. And it is difficult to estimate in such reaction or to minus C4. So, we know there are
the homogeneous reactions of oxygen, molecular oxygen with methanes, usually the statistically slow, nose high.
it's only my comment.
There is a slide with the transformation of the different oxygen species in your slide.
Is this one? No. 氧化。